the 3 gauge boson scattering amplitude. Did anyone try those? Do you really want the lights off? The lights are a bit of a disaster. Okay. Great. Anyone try to compute the 3 gauge boson? Okay. Okay. I promise you by next Monday we'll have an assignment just to get you guys working a bit. We'll have an ordered Viva session where I'll ask people at random to do assignments. Okay. 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 Great. I'm going to leave this as an exercise for you. Okay. The 3 gauge boson amplitude. Please do the calculations. It's not difficult. It just has to be done. Okay. Today we're going to talk about 4. Okay. There's actually one thing that I haven't stressed so far that I wanted to say. You see, when we got some scattering amplitude, I said, for instance, that if the pi theta x is the vertex operator for the tachyon. But you might wonder, how do I know it's this rather than some number that exists? Okay, so it's a vertex operator. So to be safe, what we're going to do, say, I'm going to put some normalization constant out here. GT times this. Okay? And we'll see how we determine all these, everything consistently. Okay? So the normalization constant for e to the pi theta for the tachyon, e to the pi theta, right? The normalization constant for the gauge boson is some G gauge boson. Now, actually, the relative normalizations between this and this can be obtained from the state operator vector. Okay? Because if we choose to normalize e to the pi kx, so that it corresponds, so it's the operator corresponding under the state operator map to a unit normalized state. And we choose to normalize this guy so that it's the operator corresponding to a unit normalized state. Then that, as we will see later on, fixes the relative normalization. But for now, as you might expect, because you're just trying to create a particular state, okay, with the same amplitude. You know, you create a unit normalized state here, either the gauge boson on the tachyon. The overall normalization has to do with the fact that that we might be working with a strangely normalized field. You know, so for instance, if you're doing scattering in 5 to the 4 theory, one natural normalization is to work with this guy. Okay? The other natural normalization is to work with this is related to this by a scaling of the phi field. Phi goes to G times phi. Okay? Now, in this normalization, the scattering amplitudes correspond to simple insertions of a phi line. Okay, because this is the normalization in which the 2-point function has a pole of unit strength. Okay? In this normalization, the scattering amplitude will correspond to phi line times a factor of G.
By phi line you mean residue around the pole?
No, by phi line I mean, yeah, right. So in this normalization, let's look at what the Green's function is. Okay? The Green's function is the inverse of the quadratic term of the determinant. So it's G squared times P squared plus M squared. Okay? So this phi doesn't create a unit normalized state. It creates a state with amplitude G. So that has to be removed away. Okay? So different normalizations of field theory Lagrangians correspond to different conventions for whether you have to put a factor of the coupling constant, actually inverse coupling constant, along with each vertex operator or not. Now string theory turns out works in this normalization. as you can see from the fact that all sphere amplitudes are of order 1 over g square. That's this overall 1 over g square. Okay? So because of that, apart from the normalization associated with the state operator map, the normalization associated with correctly getting the normalization for each object, then there's an overall normalization associated with the 1 by g square inside. Okay? So for our purposes now, we'll just keep all these normalizations completely free, use consistency conditions to determine that, and then try to interpret later on what patterns we find. Okay? So while there will be a nice logical relationship between these two normalizations, we will not use that for now. Okay? Right. So now what I'm going to do is to try to compute the 4 tachyon sketch. I'll first do it for open strings, and first ignore Chang pattern factors, then I'll put in the Chang pattern factors, and then I'll do it for closed strings. Okay? So we've got 4 vertex operators at position Z1, let's call it Y1, Y2, Y3, Y4. Okay? So, what we've got to do is choose 3 of these guys to be fixed. And the 4th guy now has to be integrated over. Now, we've carefully, in the case of 3-point functions, checked that the answer doesn't depend on the locations of the fixed vertex operators. We had a formal proof for that when studying our scattering amplitudes. I'm just, while presenting this, I'm going to believe that. So I'm going to just fix 3 of these to 3 convenient values and get the answer.
And 3 because we are taking the disk to the sphere and sphere is 3.
Exactly. You see, the conformal killing vectors were analytic. What were the conformal killing vectors? They were 1, z and z squared. Z dz and z squared dz. This vector, as well as dz bar, z bar, dz bar, and z bar squared dz bar. Now, on the upper half plane, we will only we are only interested in those coordinate transformations that preserve the boundary. Okay? So, we are interested in those coordinate transformations that do not change the upper half, the x-axis. Okay? So, suppose we've got some linear combinations of this and linear combinations of this, and you want the x-axis not to be changed. Okay, so let's do this for instance. Okay, what is this? This is delta z is equal to some constant a. This guy is delta z bar is equal to some a bar. Okay, what we want is that at y equals 0, we want at y equals 0, y not change. Okay, so what's delta y? Delta y is proportional to delta z minus delta z bar. Okay, so it's delta y proportional to delta z minus delta z bar proportional to a minus a bar. What that tells you is that a is a real number. So it cuts down the total number of similarly you can work it out with z squared and z bar squared. Okay, basically it takes what were 3 independent complex conformal killing vectors and makes them 3 real conformal killing vectors, which is exactly enough to fix the positions of 3 vertex operators on the boundary. Okay, clear? A good question, I should have said that. Okay, right. So in many ways, as we've noted, the open string behaves like just the holomorphic sector of the closed string. That counting works even for the conformal. It just basically the open string boundary conditions link what's happening in the holomorphic sector to what's happening in the anti-holomorphic sector. So if you know one, you know the other. Okay? Excellent. So, so what we're going to do is to believe that the answer will not depend on what values you fix these guys to. and go ahead and do the calculation. I'll leave as an exercise for you the direct verification of this point. It's a simple exercise, but I won't. Okay? So, the three values I'm going to choose are the following. You see, I want to choose three, I want to be able to put 3 points in convenient locations. Okay? So the first thing I'm going to do is to locate one of the points at infinity. Okay? How do I do that? I use the fact that K, the killing symmetry, the K symmetry, okay, is translations in 1 by z. Do you know this?
Special conformal.
Let me tell you about this. Okay. Suppose I want an interpretation of the special conformal transformation. Okay? So what is the special conformal transformation? The special conformal transformation actually in this analytic this context is very simple. It's just z squared L by del z. Okay? Now, let's look at what this becomes in the coordinate W, where W is equal to 1 by z. Okay? Del z, which is equal to del of 1 by W, is equal to minus 1 by W squared dW. Okay? Which is equal to, and therefore, yeah, wait. Sorry. Let me del z is equal to del W by del z, sorry, del W, which is equal to minus 1 by z squared del W, which is equal to minus W squared del W, or equivalent to del W, which is equal to minus z squared del z. Okay? So if you go to the coordinate 1 by z, then the special conformal transformation in the original coordinate is simply a translation in the coordinate 1 by z. That's a good way of thinking of special conformal transformation. This, by the way, is true in every dimension. Okay? A special conformal transformation is the generator, you do an inversion, then you translate, and then you invert back. Okay? So now infinity is a pretty strange point in the original coordinate system, but it's just 0 after you've done 1 by w. And you can always do a translation on the real axis to put any point to 0. Okay? So you use a special conformal transformation to fix one of the points to 0 in the inverted coordinate and invert back. Okay? So that set one of the coordinates to infinity. Okay? Now you've got two other coordinates on the real line. You've got two other points. This one's at infinity. I want to do transformations that will not change the fact that it will not move infinity. Which means I've used up my special conformal transformations. Because those are the guys that translate in 1 by z. What it has not used up is translations. Because infinity plus a constant is infinity. Okay? And what is not used up is dilatations. Because infinity times a constant is infinity. Okay? So you can use translations to set one of these coordinates, the leftmost guy, to 0. And then you can use scale transformations to put the middle one to 1. Okay? So this is a demonstration that you can use your conformal invariants. Note I've only used the 3 K vectors available to me. Translations, dilatations, and special conformal transformations. These were the conformal K vectors. The disk. I've used these, finite forms of these. Okay? To set 3 of my coordinates to 0, 1, and infinity. This you cannot question.
There are ordering issues.
Why are there ordering issues?
The 2 guys are sitting on the boundary.
Huh?
You can't exchange 2. So.
No, exactly right. So, suppose there are 4 guys. I'm choosing 3 of them. Y1, Y2, and Y3. I'll put Y1 to be 0, Y2 to be 1, Y3 to be infinity. And I will choose Y1, Y2, Y3 in this order. that is, I've got 4 points. I choose 3 of them in this order, and I set that to 1, 0, 1, and infinity. Now, as you say, y4 is free to be between any of these. And we will take that. y4 could be between infinity and 0, which means on the negative real axis. It could be between 0 and 1. So this is negative real axis, this is between 0 and 1, this is 1 and infinity. We will take all those into account. Those points. Okay? Fine.
Does not need full weight for this game.
What?
Can this whole exercise you carried out only say on the upper half?
Oh no. If you want to do the same thing for the closed string, you have twice as many symmetries. So once again, you can translate any point to infinity. You see, here we use the fact that we can translate any point on the real axis to infinity with one special conformity. There we have, the point could be anywhere on the plane, but we have 2 special conformities. So once again, we can translate it to infinity.
So
This can always be done. 0, 1 and infinity, even if you have the sphere. Okay? Fine.
Is it in some way important that you are using just the global part of the conformity?
Is it in some way important that I'm using the global part? You see, the global part is the only part that is well defined. See, to say it again, we're using that part of the symmetry that was left unfixed by our gauge condition. That's the only thing that's left as a redundancy of description. You see, we're using the part that we had not fixed, the part that needed us to fix 3 vertex operators. So it's very good. Okay? Great. Okay. Now, let us suppose that we're looking at tachyons. This guy carries momentum k1, this guy carries momentum k2, and this guy carries momentum k3. Okay, and as Ronak said, actually, it's true that even the cyclic ordering of k, now that I've fixed particular momenta to this guy, this guy, and this guy, I will have to sum over cyclic orderings for. We're looking at the case where k1 is before k2 is before k3. There's one more possible ordering, even if you're willing to put k4 wherever you like. Okay, so we will have 2 cases. There's k1. So let's say that we use the convention that y1 is, let's say, what do we want to say? So say we use the convention that y1 is always 0. So say y1 is 0, y2 is equal to 1, and y3 is equal to infinity. Okay, one ordering is where we put k1 to this guy, k2 to this guy, k3 to this guy. There will be the other ordering in which we put k1 to this guy, k3 to this guy, k2 to this guy. These are the only 2 cyclical orderings of 3 points on a circle. And then we will put k4 between any of them.
Why is K2, K3, K1 not different from K1, K2, K3?
Sorry, why is second? Why is
K2, K3, K1 not different from K1, K2, K3?
K2, K3, K1
Yes.
not different from K1, K2, K3?
Yes.
Because of the disk. All that matters is cyclic ordering. You want to do it?
Fixed y1, no?
What?
You already said this point is y1.
You see, suppose we had 4 points. Okay, we had the ordering K1, K2, K3, K4. You cannot use diffeomorphisms to change this order. Okay, so that while going around cyclically, let's say anti-clockwise, that is K1, K2, K3, you cannot change. Okay, so if it's this ordering, I'll fix this guy to 0, this guy to 1, and this guy to infinity. Okay, if on the other hand you have the ordering, I'm not worrying about K4 because I'll sum over all possible. Okay, if I have this ordering, then I'll fix this guy to 1, 0, this guy to 1, and this guy to infinity. Is it clear? If this was confusing, let me say it again. you see, what did we have? We had a scattering amplitude on a disk, and we had particles coming in. These particles carried momentum K2, K1, K2, K3, and K4. Okay, what we're supposed to do is to look at all possibilities of orderings of K1, K2, K3, K4, K1, K3, K2, K4, and so on. These cannot be changed by diffeomorphism. With a particular ordering, then you can fix the points. Is this clear? Okay, so since I'm going to sum over Y4, like the K4 guy being anywhere, we only need to keep track of the cycling orderings of K1, K2, and K3. This clear? Yes.
Shouldn't the 0 be adjacent to infinity in that case?
It is adjacent to infinity. Adjacent like this.
No, if you put the K4 somewhere in between K1 and K3, then it won't be adjacent.
No, I mean, it's, why do you say that? Okay, let's look at how the real. We've got this real line. 0, 1, infinity. This is also infinity. Okay. How does this map up? It's identifying this point. Okay, that's the disk. So K4 could be here. Yeah. Okay. Is this clear? Okay. So fine, let's start with one of the calculations that we can sum all of the things. Very easy. Okay. So let me take the case where K1 is at 0, K2 is at 1, K3 is at infinity, and K4 is wherever we want. We look at all possibilities. Okay? So let me start with, just to be totally concrete, let me say that K4 is between 0 and 1. Okay? It's some number Y, which let's in our mind fix to be between 0 and 1. We'll have to fix. We'll have to choose one. All options. Okay? Now what we need to do is to compute the worldsheet coordinate. So, what do we have? Firstly, we had C of Z1, so the C insertions, which was Z12, Z23, and Z13. Okay? Now let's see. So Z12 was 1 minus, sorry, let's say 0 minus 1. Because 1 was 0 and 2 was 1. Z23 is more violent. It's 1 minus infinity. We'll imagine that infinity is some very large number which we'll regulate. You can fix that not to be infinity or something large. Okay. 1 minus infinity and Z13 is just infinity. It is 1 minus infinity. 0. Okay. Then, what did we have? You remember our formula, somebody will have to remind me of the factors of 2. But we had the formula which was y12. Actually, these should have been y's. Okay. Y12 to the power alpha prime 2 K1 dot K2. Can somebody confirm the 2? Correct, right? Mod Y12, mod Y13, the power 2 alpha prime K1 dot K3, Y14 to the 2 alpha. Well, alpha prime K1 dot K4, Y23 to the power 2 alpha prime K2 dot K3, Y24 to the power 2 alpha prime K2 dot K4, and Y34 to the power 2 alpha prime K3 dot K4. Now the strangest thing about this whole formula is that there are plenty of infinities around. Right? And they bear cancel. So let's first check the cancellation of infinities and then look at the finite. So this object here, we won't get the minus very much, but okay, I get overall sign right with the consistency. Yes.
Plus infinity and minus infinity are identified. How do you know that you have to put number at plus infinity there?
Yes, how do I know that I have to put plus infinity? So, right? Yeah. You see, they identified at the same point on the disk, but they're different points on this line. Now that sounds very strange, right? That's very strange. You know, in the end, it will not matter. It will not matter because every factor of infinity here will cancel with another factor of infinity here. Okay, so whether it's positive or negative, this will not matter. Okay, whether it's plus infinity will give you the same answer. It's a good question. It's confusing. This is actually a bad representation, but it's calculation convenient. So let's see. But it's a good question.
Which point is identified with minus infinity on the list? I mean, is it the same as plus?
Same point. It's just one point. You see, think of it like a stereographic projection. So,
you say moving clockwise around the disk is counterclockwise around the disk is like moving the positive axis and
correct.
Counterclockwise is negative.
It's like this. This whole disk here. It's think of it like a stereograph.
It's just open.
This point is here as well. Right. Yeah, it's exactly just open. Okay. So now let's look at which guys will involve infinity. It's the guy with the three fingers. Okay. All of them will be infinity. So we get infinity to the power. So we had infinity here to the power 2. Didn't matter whether it was plus or minus. And we had here from here infinity to the power 2 alpha prime into everything that involves k3. But everything that involves k3 comes with a k1 plus k2 plus k4. But k1 plus k2 plus k4 is equal to minus k3. So k3 dot k3. No, not much that like. It was fastest we did trouble. So, what was the Marshall condition? Okay, the Marshall condition was that m squared was equal to minus 1 by alpha prime. Was equal to m squared was minus 1 by alpha prime, but m squared is equal to minus k squared. So k squared is equal to 1 by alpha prime. Okay, and so this cancels this. Okay, so the infinities cancel, and it also tells us that it simplifies the formula a lot. Because everything involving a 3, this part, the part that didn't involve a 3 is just some plus or minus 1. Okay, everything involving a 3 from here is 1. So all that remains are things that don't involve. Okay, so what remains? y12 remains, but y12 was 1. So 1 to the pi anything is 1. Okay, so that doesn't really remain either. What remains is y14 and y24. Okay? So, what was y14? y14 was 1 minus 4. Everything's mod, so it's 4 minus 1. So, if we just call the location, if we just say that y4 is equal to y, then we get y to the power 2 alpha prime k1 dot k4. Right? and we get 1 minus y to the power 2 alpha prime k2 dot k4. And we have to do the integral dy. Is this clear? Okay, that's a pretty simple formula. I'm going to remind you how to do such integrals in a minute. So before we even process the integral, let me write in terms of invariance. Okay, so suppose we have k1 plus k2 the whole thing squared. Now this should be plus or minus this squared. Minus s squared, because we're using the mostly positive. So there is like energy would be minus s. K1 plus K3 all things squared is equal to minus 3. K1 plus K4 all things squared is equal to minus 3. The standard kinematic variance was getting. Okay, then this guy here, let's look at k1 dot k4. K1 dot k4 is equal to k1 plus k4 the whole thing squared minus k1 squared minus k4 squared by 2. So 2 alpha prime k1 dot k4 is alpha prime times this. Okay? And then we have k1 squared is 1 by alpha prime, and k1 plus k4 the whole thing squared was minus u. So this is equal to minus alpha prime u minus 2. Is this clear? In the same way, this quantity is k2 dot k4, which involves k2 plus k4 the whole thing squared. But by one to constellation, that's the same as k1 plus k3 the whole thing squared. Yes, it will be the same algebra. Minus alpha prime t minus. Okay? So this integral here becomes integral dy y to the power 2 alpha prime minus alpha prime u minus 2 1 minus y to the power minus alpha prime t minus 2. Is this clear? Okay. Now, before we evaluate any one of these, which is easy to do, but before we evaluate any one of these, what we're going to try to do is to look at all the orderings. Okay? So, suppose, for instance, so there are 6 possible orderings, because there's the location of y4 between 1, 2, 3, and then there was the possible cyclical ordering of. So what has this part done? This part has taken into account what ordering? It's taken into account the ordering k1, k4, K2, K3. Okay? This ordering gave us this answer. Now, suppose we have any other ordering. And choose a random ordering. Let's say K4, K3, K1, K2. We're going to get the same answer with the appropriate replacements. With K1 goes to K4, K4 goes to K3, and so on. Do you see that by doing this, what we will generate is every possible pair of bilinears? Okay? So for instance, this ordering will generate what? We had K1.K4, that will become K3.K4. Okay? We had K2.K4, that will become K2.
K1.K3.
Sorry, you're right. K1.K3. K1.K3. Okay? So this guy will be K3 plus K4 the whole thing square, which is same as K1 plus K2 the whole thing square. So we give us an S. Okay? And this guy is K1 plus K3 the whole thing square, which is a T. Okay? So if I call this guy.
When did we decide K4 was to be between K1 and K3?
I decided that because I said Y was between 0 and 1. I choose one of them.
Yeah.
Okay? So, yeah, so 0 to 1. Okay. So suppose I define some function. And by the way, there were 6 possibilities, but there are only 3 choices. Okay. So what will we get? What we will get is, suppose I define B of S, T, U. Okay, let me say that this is. Sorry. Let me call this B of U and T to be dy y to the power minus alpha prime U minus 2 1 minus y to the power minus alpha prime T minus 2. Suppose this is B of ut. Then you see what you're going to get is that the full answer will be B of ut plus B of st plus B of su plus 6 possibilities. B of, I should have done systematically. Okay, D. I've got one U here, so U and S plus B of second, okay, so DU plus B of T S. However, under the variable change y goes to 1 minus y, it's totally clear that B itself is symmetric under unity.
For each B, will the limit of integration remain the same?
Will always be 0 to 1. You see, you can do the calculation in a way that it makes the integral look like it's between 0 to infinity, for instance, or 1 to infinity. But you'll always be able to perform a variable change to map that once again to 0 to 1. See, we've given a physical argument for that. Because each ordering is the same. You may represent it in a different integral. Okay? But you'll always be able to change variables to do that. I'll show you one example, for instance. Okay, but let's first get this. Yeah. So, I'll show you an example in a minute. Okay. Maybe I should. Okay, but first let me just say this. Okay. So, great. So, this is just equal to twice of B of ST plus B of UT plus B of SU. So all we have to do is compute this integral once and then sum over these 3 possibilities and we've got the full answer. the sum over three possibilities is very closely analogous to something that happens in quantum field theory. That is, if you've got a Feynman diagram involving exchange, you can exchange between K1, K2 and K3, K4. Or you could exchange between K1, K3 and K2 and K2, K4. Or you could exchange between K1, the other one. K1, K4 and K2, K3. These graphs are sometimes called the diagrams of the S channel, the T channel and the U channel, because the poles appear in the variable S, T and U respectively. And so what we see is that open strings behave very much like that. Okay? You will have some object in the S channel, an object in the T channel, object in the U channel, you have some three separate components. As we will say as we go along, closed strings will behave much more clever. There will be because there's no analog of the cyclical sum. Right? There are no options for closed strings. It's just one answer. Closed strings will involve one object, which when expanded one way will have all the S channel poles, and expanded in another way will have the T channel poles, and expanded in another way will have the U channel. Closed strings is much cleverer than open strings. Okay? So the open.
But when we are not having any exchange, this is a tree level.
This is a tree level, but you will see this is 4-point tree level. So you will see as we go along that you will be able to take this tree level thing and factor that into any sum over poles corresponding to 3-point propagation 3-point. And one of these guys, this guy will give you all the poles in the U channel. This guy will give you all the poles in the S channel. And this guy will give you all the poles in the T channel. Hang on a few minutes. Okay? Yeah. Now, let's get to Anandi's question. Anandi's question was, it didn't seem like when y4 was between 1 and infinity, you would be an integral between. It didn't seem like between 1 and infinity. It didn't seem like that. So let's check that that this slick argument is actually getting it right. Okay. So let's work through the ordering. K1, K2, K3, K4, and our original representation was adapted to that ordering, just requiring us to integrate y4 between 1 and infinity. So it was the same formula here, but with y4 integrated between 1 and infinity. Is this clear? Okay. So notice that the original guy was K1, K2, K4, K3. So if our prediction was correct, what is this doing? K1 is going to K1, but K2 is going to K4. So we have, so K1 of this formula is going to K1, K4 is going to K2. Okay, K2 is going to K4, and K3 is going to K3. So what should it have been? It should have been, so K1.K4 should have become K1.K2. So U should have gone to S, and K4.K2 goes to K4.K2. So T goes to T. So it should have become a B ST. Let's check that that's correct. Okay. So that's the question of whether dy y to the power minus alpha prime u minus 2 1 minus y to the power minus alpha prime t minus 2. I'm doing this integral now between 1 and infinity. I want to convert this integral to an integral between 0 and 1.
If we get about science.
About science?
Yes.
So both of these separate quantities, that should be y minus
Right, y minus 1. Thank you. Okay, I want to convert this to an integral between 0 and 1. There's an obvious way to do it. Make the variable change, y goes to 1 over y. Okay, so let's say that y is equal to 1 over w. Okay, so we get minus dw by w square. Am I doing this wrong again? dy square. Right, because dy is dw by w square. No, sorry. Sorry. Dy is dw by w square. Correct. Okay, then we had y to the power minus alpha prime minus u, so that becomes w to the power plus alpha prime u plus 2. And we get yeah. Now 1 by w minus 1 to the power minus alpha prime t minus 2. Now we put this up here. Okay, so that becomes minus dw by w square. The minus, of course, will go away in the change of limits. So that's plus. This is w to the power alpha prime u plus 2, and this is 1 minus w to the power minus alpha prime t minus 2 divided by w to the power minus alpha prime into w to the power alpha prime t plus 2. So the power w is w to the power alpha prime u plus t plus 4.
Minus 2. Because of the one.
Minus 2, so plus 2. Okay. And then what do we know about x plus t plus u? S plus t plus u is equal to 4m square. Which is equal to m square was minus 1 by alpha prime. So alpha prime s plus t plus u is equal to alpha prime, which is equal to minus 4. And therefore alpha prime t u plus t is equal to minus 4 minus alpha prime s. So this becomes w to the power minus 2 alpha prime s minus 2. So it's exactly the same integral as before, with t in place of t, but it's s in place of u. Okay? So, though we got this physically, you can easily check that each of these is working.
Or every time I can just change which points I set to 0.
Exactly. This is just to check that it doesn't matter which points you're setting to 0. Yeah, that's effectively what it's a check of. Okay? Excellent. So now that we've got this answer, let us try to focus on this object, this b of u and t. I'll call it b of s and t. Okay? Instead of u with s and t. S and t. I don't know. I'll call it b of x and y. So let's call it b of x and y. B of x and y is equal to dy y to the power minus alpha prime x minus 2 1 minus y to the power
b of x and x prime.
y, thank you. N minus alpha prime b minus 2. Okay, what can I say about this object? Now, some of you know what this integral is, right? First, I'm going to remind you of the formula of the beta function. Okay? So, let me remind you of the formula of the beta function. In fact, I should call this b because this b is the beta. So let's call this c. So b of ab is equal to 0 to 1 dy. Why is it so hot, by the way? Somebody mind switching the fan on? Yeah? Yeah. D by y to the power a, 1a minus 1 minus y to the power b. Okay. And let me remind you that this beta function can be written as product of gamma functions. Okay? So I'll remind you how that works. So, suppose we define y is equal to v by w. Okay? So then we find that, suppose we do this. We treat w as fixed and v is the integration. So we're just doing a variable change. So y is v times v by w, v is the integration variable, and w is fixed. Okay? So what do we find? We find that beta v is equal to dv by w into v to the power minus 1 by w to the power minus 1. And now this becomes w minus v to the power v minus 1 over w to the power v minus 1. Okay? So we have w to the power a plus b minus 2 v of ab is a integral dv v to the power a minus 1 w minus v to the power v minus 1. Okay, so far so good. Now what we do is to take both sides of this equation and multiply by e to the power minus 1. Okay? And then we integrate this equation. We integrate the equation from 0 to infinity. So this v was 0 to 2. This integral was 0 to 2. This integral was 0 to infinity. Okay. So the left hand side is just the definition of the gamma function. Okay, the left hand side is the definition of the gamma function of what? Of a plus b. Wait, I messed up. There was w. So there's no minus. Okay, yeah. So the left hand side is just the definition of gamma beta. Because gamma of alpha is w to the power alpha minus 1 integrated e to the power minus 1 to 0 to 0. Okay. What about the right hand side? The right hand side is a product of gamma functions. And the way to see that is that we shift variables to w minus b and to v. You see, what this is doing is covering the whole plane where v is greater than, where w is greater than v. So if we shift variables to w minus v and v, these two variables are integrated independently from 0 to infinity. Okay? And then each of them becomes a gamma function because what we had was e to the power minus w, which you can write as e to the power minus w minus v times e to the power minus v. So this e to the power minus w was the exponential needed to get a gamma function for each of the two things. Okay? So b AB is equal to gamma of a Okay? Times gamma. So this beta function we just proved. Beta AT is equal to gamma A, gamma over gamma. Gamma functions I don't need to remind you of, right? Gamma functions we all know. Gamma functions are the things such that gamma can plus 1 is n factorial, gamma of 0 and every negative number is a pole, and you all know these gamma functions. Okay? So now that we've expressed this beta function in terms of gamma functions, we understand the analytic structure for this function very well. Okay? Now all we have to do is to relate what we had, our C's, to the beta. So that's very easy. Because our C was simply, our C of AB was simply B of minus alpha prime x minus 1 minus alpha prime y minus 1. This y here?
Y is integral.
Here, you wanted this to be this number to be something like
The
that?
C function. The integral is over.
The integral was 0 to 0. Oh, yeah. That in the C function that was defined to be 0. Remember we answered Anindita's question about how vertical range is equal to 0. Right, so this C, this is 0. Right. The values of A you might worry about. A and B have no particular restrictions. Gamma functions are defined as functions of the complex. Okay? So physics we may be particularly interested in some values. But this definition gives you a function for arbitrary A and B. Okay? Some points they are plane, they are poles. I mean, those poles will learn because. Okay? Excellent. So our full tachyonic scattering amplitude. Our full tachyonic scattering amplitude was gamma, actually factor of 2. And then we should keep track of all the normalizations. I'll do that. Normalizations we need to be careful with these things. But gamma of, so what was the rule for beta function? Just product of these two divided by sum. Gamma of minus alpha prime s minus 1, gamma of minus alpha prime t minus 1 by gamma of minus alpha prime s minus alpha prime t minus 2 plus gamma of minus alpha prime s minus 1 gamma of minus alpha prime u by gamma of minus alpha prime s minus alpha prime u minus 2 plus gamma of minus alpha prime t minus 1 gamma of minus alpha prime u minus 1 by gamma of minus alpha prime t minus alpha prime u minus 2. Okay? This is the full formula for the scattering of 3 Chan pattern or 4 Chan pattern lists. Yeah, they can be simplified, but it won't become of this form because there will be an additional minus. Okay? Yes. So you can simplify it as Mangesh said. For instance, let's take this term using S plus T is equal to minus u minus 4 alpha prime s plus u to minus alpha prime u minus 4 yeah, so the 2 will become a plus 2. right? So this could be written as gamma of alpha prime u plus. Yes, absolutely. Now let me first check. What's that then? Yeah. Exactly. Excellent. Looks good. Okay. Fine. So now what we need to do is to start studying some of the start trying to understand some of this kind of stuff. Okay, so let's take one of these guys. Let's say the guy with let's say that we take the guy with T and E. So let's focus on this one. Let's take the guy with gamma of minus alpha prime E minus 1. Gamma of minus alpha prime U and gamma of that's why I get it from ratio today, alpha prime S okay. Now various things about this amplitude that we want to understand. The first of these things is where the poles are. Suppose we look at this chart and we ask where its poles lie. Okay, so how do you get poles in an expression with gammas? We get poles when their arguments are negative integers. Okay, in this expression, if S becomes a negative integer, we get a pole of the denominator, which is a zero of the function. So we're not interested in S becoming a negative integer. Yeah, what we're interested in is, let's say, T becoming a negative integer. So actually, so let me just look at the one with this S. Okay. So suppose we look here, and we ask, where do we start getting poles? So minus alpha prime S minus 1 is equal to 0. Is the first location of a pole for a gamma function. Okay? Now where does that happen? This occurs at minus alpha prime s is equal to 1. So alpha prime s is equal to minus 1. Okay? But now, in quantum field theory, when you have a pole, when you have poles, you've got poles but you've got exchange particles. What is the location of the pole? S is equal to the mass square of the particle. Okay? So what is m squared equal to minus 1 there? It's which mass? The tachyon. So you see that this first pole occurs precisely where you should expect the pole associated with tachyon, tachyon goes to tachyon, goes to tachyon, tachyon. Now, you could ask, does this diagram exist? Well, it exists provided there's a tachyon, tachyon, and tachyon with it. But we computed that last class. It was non-zero, it was 2 in some normalization. Okay? Fine. Now, the next thing we want to do is to compute the residue. Right? So let's compute the residue. So, what we have here is, let's suppose that we have S is equal to this quantity, minus 1 by alpha prime. Okay. Now, how do we estimate gamma of a very small, gamma of 0 as a pole? How do we estimate gamma of very small? We do that as follows. We know that gamma of x plus 1 is equal to x times gamma of x. And therefore gamma of x is equal to gamma of x plus 1 by x. If x is very small, this is gamma of 1, which is just 1. So this is equal to 1 by x. So gamma of x at small x goes like 1 by x. Okay? So this quantity when we're near the pole is when we're near the pole, goes like 1 over alpha prime s minus or plus 1. That's what it is. Okay? Now what we've got left here is gamma of minus alpha prime t minus 1 divided by gamma of alpha prime u plus 2. But what do we know? We know that alpha prime s is equal to minus 1. And we know that alpha prime s plus alpha prime t plus alpha prime u is equal to minus 1. This was minus 1. Okay? So alpha prime t plus alpha prime u is equal to minus 3. And therefore, minus alpha prime t minus 1 is equal to alpha prime u plus 2. And therefore, you see? So, in fact, the residue of the pole is very simple. It's just a pure number. Why did we know it had to be so? Why did we know it had to be so? Because this is unitary. You see? Or we believe effective field theory. Oh, these guys are. Oh my. You see, let me just say this. You see, if this 3-point coupling.
Already there is idea.
I'll leave it. If this 3-point coupling here, okay, has a certain dependence. It's this 4-point thing, the factorization of pole, is precisely 3-point coupling square divided by pole. But we knew from our previous calculation that 3-point coupling square is just a number. It's not a function of momentum. So what we had to get was one of the pole with no function of any momentum. Didn't look like it. Turned out. Okay? Next class we will continue to analyze this in more detail, and we will then compare the numbers, and we will work this out in great detail. This and the closed version. Okay, I'm sorry. Sorry, I started the class late. I don't know.
There will be an infinite number of codes.
Oh yeah.
So this is the first thing that we have seen.
This is the first thing. The next one will be which one?
In S channel it can be I minus alpha prime is minus 1 equal to minus 1.
Yes, and what do you think that particle? What?
What's this?
Photon. Yes.
So one straight
You see, because we know that there's an accurate photon vertex, the computer in that case. Okay. No, it's exams. We know that